Thanks for the introduction. And hello, everyone. My name is Qian. I'm from the University of British Columbia. I'm glad to be here today to present our work on the depth and size perception of a spherical fish tech VR. So in this study, we evaluated the spatial perception provided by a spherical fish tech VR by comparing it to a standard flat fish tech VR. And we showed that the spherical shape of the screen can potentially improve the depth and size perception in 3D. So as an introduction, spherical displays have been widely used in many areas, such as planetarium and museum. So as a display, it has several interesting properties, such as it can provide unobstructed view from all angles as people walk around it. And it's a display with finite volume. So its enclosing shape naturally indicate the scale and the position of the object inside. And at last, due to its isotropic surface, it does not have any sweet spot as people walk around it, compared to traditional flat displays. So these properties are ideal for fish tech VR. So in fish tech VR, we track the user's position using a head tracker as people walk around it. And then we render perspective-corrected imagery on the surface of the display to create an illusion. So in this case, the spherical screen creates a 3D illusion as if the 3D object is inside the volume. In the past, there are several work have been built the several different spherical prototypes. And using these prototypes, a number of interaction techniques have been proposed to leverage the nature of spherical display. Effective interaction techniques depends on accurate perception. However, it is unclear from the previous literature on the fundamental spatial perception provided by the spherical fish tech VR. So taking this spherical display as an example, so we can see like very clearly the basket of fruits, even if it's just seeing stationary. And as we can see, although we just see stationary, we can still see as if those fruits exist in the real world. So in this case, the spherical screen itself has a geometry indication that convey the spatial location of the virtual object inside, and it as if it exists in the real world. So its physical representation conveys the kind of like the geometry information. For example, we kind of can know the size of the apple with respect to the display. And so this brings us to the question, if we render the exactly same content on a flat display, will our perception still be the same? In other words, will the geometry indication provided by the screen shape alter our perception? So to investigate this problem, we first implement a spherical fish tech VR. So the system itself is made by 4 projectors as a spherical screen. And we use shutter glasses to provide stereo vision tracked by an EM tracker. And then the display itself is auto-calibrated using an calibration approach to blend multiple projections. And then we further use perceptual viewpoint calibration to register the viewpoint of each user. Once calibrated, then we can render perspective-corrected imagery on the display based on the viewpoint. We then use this implemented system to conduct a user study to evaluate the spatial perception provided by the spherical fish tech VR. We compare the performance of this spherical fish tech VR to a traditional flat fish tech VR. Both those two systems are implemented with the same hardware, like same projector, same tracking system, and calibrated using the same procedure. In both display conditions, the viewer will sit facing the display with a fixed viewing distance. They can move their viewpoints by leaning their body from left to right while keep seated. And then we evaluate the depth and size perception using 2 tasks. For the depth perception, we use a depth ranking task. So in this task, user will report the depth of the virtual ball with respect to a depth axis that points away from them. And then there are 12 tick marks on that depth axis, and the user will choose which tick mark they feel is closest with respect to the pool ball. And then for the size perception, we use a size matching task. User then will adjust the size of a virtual ball to match the size to a real ball. We hypothesized that in both tasks, the absolute error will be lower on the spherical fish tank VR compared to a flat fish tank VR. And we recruited 16 participants in a within-study design by having the participants to try both display in a counterbalanced order. And they will first have a practice, then depth task, then size task. And in both display conditions, the virtual ball will located within 3 different depth regions as near, mid, and far with respect to the user. And here's a result. So we found that for the absolute error, in the depth ranking task, the absolute error is significantly lower on the spherical fish tank VR compared to the flat fish tank VR. Likewise, in the size task, the absolute error is also lower on the spherical fish tank VR. While this result is significant, what we can also see is, in fact, the difference between the spherical fish tank VR and the flat fish tank VR, the absolute error is rather trivial, with only the difference as 0.8 millimeter. So this may indicate that the benefit of having a spherical display for the size perception isn't that obvious. However, the absolute error as a metric may not accurately represent our size perception. So if we think about it, in reality, the size perception is always closely related to the depth perception. That's why we may say some object that is further away looks smaller. And in reality, beyond that, we have size constancy. That's why I would say, so regardless of the distance between me and this virtual pool ball, I will always say like the pool ball have the same size, independent of the distance. Let's say even if this pool ball is further away from me, the retina image is smaller in my eye, but I still say it's the same size. But in the virtual world, it may not be true, especially if we consider we see the screen, not the object. And in fact, when the virtual object is further away from us, its projection on the screen is actually getting smaller. So we want to investigate that size constancy in the virtual world as well. So we use a size ratio as a metric instead of the absolute error. It's defined as the ratio between the size of the virtual ball, set by the participants, divided by the size of the real ball. And then when the ball is moving further away from us, having the size constancy means the size ratio will always be a constant of 1 with 0 slope. However, if we perceive the object's size not based on its actual size, but rather based on the projection size or retina image size, then the size ratio will increase with a positive slope. And if we plot all of the size ratio in both display conditions and fit them with a line, we'll find that the spherical fish tank VR actually has a better size constancy compared to the flat fish tank VR by having a significantly lower slope. So this result indicates that the strength of having a spherical display for the size perception may not reflect as higher accuracy, but rather as better consistency. And more results and analysis on the consistency can be found in our paper. As a conclusion, we found that the spherical fish tank VR can provide less depth error, less size error, as well as better size constancy. And the study indicates that the spherical display can be potentially used in 3D applications that need to accurately show the position and size of the virtual objects. So applications such as computer-aided design and 3D games might benefit from the spherical displays. And as a future work, so one of the limitations in our study is that we use a spherical stimuli due to its isotropic property. And it remains to be a question as whether other stimuli shape, like cube or cylinder can reproduce similar results. So in the future work, we plan to extend this current study to other display shape together with different stimuli shape, so that this also help us to understand the relationship between the display shape and its content. In addition to that, we still don't know how will each property of the spherical shape can individually affect the performance. So future work is required to understand the mechanism that may cause this difference. So thank you very much for listening. That's pretty much the end, and I'm open to any discussion, questions.
I'll get things started off. So one of the things I thought was interesting is the stimulus you used was a pool ball, which is also spherical. Do you think that sort of priming of looking at the spherical display and then seeing the pool ball and also the physical pool ball next to it had an impact on your results?
Yeah, definitely. That's why we also put it as a future work, saying to explore different shape of the stimuli. And in particular, like the spherical stimuli is chosen due to its isotropic properties, so that when you set the size, you make sure like participants are set based on its actual size, not like a 2D or 1D feature. For example, if you use a cube, then it's possibly they just set based on the length of the edge, right? So that's our own reasoning for choosing a spherical stimuli, but I think as a future work, it's definitely worth trying with other shapes of this stimuli.
Hi, sorry, it's not so much of a question, but actually we've looked at depth perception errors using spheres and other objects in flat screen displays. Afterwards, could we have a chat? Because I think there might be some natural overlap.
Oh, sure.
Thank you.
Yeah, thank you very much. Okay, yeah. Thank you very much. We're also doing poster presentation tomorrow and on Wednesday, so if you want more discussion, I'll be there for you. Thank you very much.